Good day, ladies and gentlemen, and today I want to pick up where we left off in some of the lessons we've been doing in class, where we're going to compare features of quadratics. And we're going to look at the many different ways there are to do that. Quadratics are the foundation for all nonlinear behaviors, and everything after a linear equation, the entire universe of mathematics, is nonlinear. So it's so incredibly important that we get a good start. Quadratics, ladies and gentlemen, can be observed through their equations, their tables, and/or their graphs, and we want to be able to see the same features in each of those presentations. That way we can have more powerful methods of investigation, depending upon what it is we're looking for in a real-life scenario. There are many instances where we're looking for the vertex or the turning point. It usually represents the maximum, the highest, or the minimum, the lowest value in a relationship, depending upon whether or not the quadratic is going up or down, and that'll be one of the features that we focus on. It's important to understand that a quadratic, ladies and gentlemen, is an x squared relationship to second degree polynomial. So as soon as you see an expression that has x squared in it, that's going to be a quadratic. In addition to that, you should be able to notice that the coefficient for the lead term, the highest exponential term in a quadratic, will belong to x squared, and that coefficient will tell us if the relationship is going up or down. If a is positive, it's going to be increasing or going up throughout time. If it is negative, it'll be decreasing or be going down. The C coefficient in standard form is the y-intercept, and the y-intercept will tell us the value of the relationship at time 0. We want to be able to make those observations in many different spaces. In a table, to be able to find the vertex, we're going to look for the point in time where the measured amounts, the outputs of the y values, are going to be repeating on either side. That's going to indicate that it either reached its highest or its lowest point, and it's either going to, at that point, go down after it had gone up for a bit, or go up after it had gone down. The symmetry of the sameness in the table will tell us where the vertex is. The x variable for the vertex will always be the unit of time when it occurs, and that's known as the axis of symmetry or sameness. We can find those relationships on a graph by focusing on the turning point. The turning point will also tell us where the vertex is. In this indication, on the graph, the turning point where the vertex is happening 2 units time ago to measure amount of -5. Exactly what we saw on the table. The axis of symmetry is the imaginary vertical line that cuts the relationship in half. Once again, that tells us when the vertex is occurring, when a relationship is reaching its highest or its lowest point. If we were to make an imaginary vertical line to go through the turning point, we should know that vertical lines cannot be represented as y equals mx plus b. They're not functions. There's an infinite number of predictions at that point in time, and they're going up so infinitesimally quick that its slope is indescribable. For this specific relationship, since 2 units of time ago is when we could split the parabola in half, we would identify it as x equals -2. All of those observations can be also made algebraically, and algebraically, to determine the axis of symmetry and the vertex, we would use a very powerful formula determined from calculus. X equals -b over 2a. The unit of time when the vertex occurs will be the result of the opposite of the b coefficient divided by twice a. That's going to require you to identify the coefficients a, b, and c, and to substitute them in appropriately. If you were to substitute into the formula appropriately for this relationship, you could determine that 2 units of time ago, the relationship reached its highest or lowest point. To determine what it measured at that point in time, you'd have to substitute -2 in place of x into the original equation. So we're taking our original function and we're putting -2 in place of x and evaluating the expression on our calculator. Don't be surprised when it says the relationship reached its low of a measured amount of -5 at that time. That allows us to identify the vertex as happening 2 units of time ago and measuring -5. And we're getting the same results as what we would have seen in our graph as well as in our table. And you want to get good at interpreting all three. Down below, we had talked about this question in class, where I gave you the scenario of a national pumpkin launching competition called pumpkin chunking, where we had catapults. And the catapults were 3 different types, labeled frightful flight and mathematically identified as f of t, go far, identified as g of t, and hopeful launch as h of t. Each of the different catapults launched pumpkins at a different rate and in a different path throughout time. So we wanted to observe those paths and rates and see if we could identify them algebraically as well once we saw their equations in just a moment. As we began our investigations, we started by looking at hopeful launch and its initial amount. Its initial amount is how far the catapult arm had been pulled back before it was launched, and it was pulled back to be about 20 feet high in the air. So you can imagine that would be a pretty large mechanism. As the arm was 20 feet in the air, it was then swung, and the pumpkin reached a maximum height of approximately 74 feet. That was our best guess, after what looked to be about 2.5 seconds. We were able to identify the domain, that blue section of the x-axis, as the time that it was in flight. And we said that that seemed to be about from 0 to 5.5 seconds before it hit the ground. We then did the same thing for go far, and we noticed that go far was brought back its arm to about 10 feet high in the air. And having pulled its arm closer to the ground, it was able to go a little bit higher and a little bit further. We identified its vertex as happening at about 3 seconds at a maximum height of about 100 feet. And we believe that its domain, how far or how long it had been in flight, I should say, identified by the highlighted green section, seemed to be approximately 6 seconds. So we said from 0 to 6 seconds. Lastly, we took a look at frightful flight. And frightful flight's catapult was able to be brought or pulled back all the way to the ground And because it was pulled back all the way to the ground, there was so much torque and tension in the catapult, it really launched the pumpkin super far. After 4 seconds, it appeared to be about 143 feet high. That was its vertex, or its maximum height. And we identified that its domain, the time that it was in flight for, d comes before r, x comes before y, so domain refers to the x-axis, and 90% of the time the x-axis is time, seemed to suggest that it was flying from approximately 0 to 8 seconds. We were then able to take those graphical or pictorial observations or geometric observations and make some table observations as well to see those same details. So when we looked at Frightful Flight, the one that was pulled back so far, by investigating its table of values, we saw that after 4 seconds, it does in fact reach 144 feet, and that is its vertex. And we noticed it was its vertex, it was the vertex in the table, because there was symmetrical or same measured amounts on either side of the table. And that matched what we approximated in our graph. So our picture matched our table of values. Now that we have the equation to be able to make these observations, we could have graphed it. That would require you to go to your calculator. It's a good idea to clear it out to make sure that there is nothing else in the memory. And if you were to do that, you would then want to go to your function list. And in your function list, you could substitute in negative 9x squared plus 72x. And if you graph this, you probably wouldn't see terribly much because our domain and range aren't set up to match our worksheet. So you'd want to go to your window and adjust them appropriately. Our domain, according to our worksheet, goes from 0 to 8 seconds along the x-axis, while our range, measuring how high the pumpkin goes from 0 feet high up to potentially 220 feet. If you adjusted your calculator screen appropriately and then graphed it, you could get a really good presentation of what we're seeing on our worksheet, as the pumpkin is flown through the air for 8 seconds and reaches a maximum height of 44 feet. By making observations in the table, we could suggest that the axis of symmetry, the time when the vertex occurs, is 4 seconds. We could then write out the vertex as 4, 144. After 4 seconds, it reaches a maximum height of 144 feet. And we can also see some other features, such as the roots. The roots are where it measures 0. And it's measuring 0, or it hits the ground, at time 0 when the arm has been swung all the way back to the ground, as well as 8 seconds from now when it hits the ground. The zeros are also called the roots of the x-intercepts. Roots are where a tree digs into the ground, and in this instance, it's when the pumpkin hits the ground, and for this particular catapult, it's when it was swung all the way back to the ground. 0, 0, at time 0 it measures 0, as well as 8 seconds from now it measures 0. If we did the same thing for g of x, ladies and gentlemen, we'd be able to observe the table of values, and we would see that at 3 seconds it reaches its maximum height. And at 3 seconds it reaches its maximum height, or we're able to determine that in the table because we see the symmetry or the same measured amounts on either side. That's going to match what we saw graphically, because graphically we noticed that for g of x, it appeared that after 3 seconds it was reaching its maximum height. We approximated it to be 100, and it is exactly that. So from the table we can see that after 3 seconds we reach a maximum height of 100 feet. The axis of symmetry is simply the time when the vertex occurs, and that's when x equals 3 seconds into the flight. We can approximate the roots. The roots are a little bit tricky because when it digs into the ground, there is no initial root, there's only a y-intercept. The y-intercept says that at time 0 it measures 10, but it doesn't go all the way back to the ground. That would be a negative time, that'd be a little weird. But it does in fact hit the ground a little after 6 seconds. So we can approximate the root as happening on an interval of time, somewhere in between 6 and 7 seconds. We're not precisely sure. Our calculator could figure it out at some point when we learn how to do that. For now, it's good to know that because we're graphing t squared, it's quadratic. Because the lead coefficient a is negative, the relationship is going to be decreasing or going down. The y-intercept from standard form is simply the numerical value at the end of the relationship, and that is 10. At time 0 it measures 10. If you want to make these investigations on your graph, you could go to your function list, and you could substitute in negative 10 x squared plus 60x plus 10. And assuming you've adjusted your domain and range appropriately, you can see the flight of this catapult. So we've got go far now represented along with Frightful Flight. As we continue on, it's important to understand that we will see the same, we'll have the same opportunities to investigate Hopeful Launch. And for Hopeful Launch, if we just focus our attention on the table of values, we notice that at time 0 it measures 24. That's the y-intercept. If you make your investigation into the algebraic presentation, you would have noticed that c is 24. And in standard form of a quadratic, c represents the y-intercept, the value at time 0. So what we're seeing in our table matches what we're noticing algebraically. Additionally, we knew that it was quadratic because there was a t squared, and the lead coefficient a was negative 8, so it must be going down. What goes up must come down. And we are seeing that the measured amounts are increasing up till the pumpkin gets to a height of around 72 feet, and then it comes on down. Now, pumpkins don't fly straight across the sky horizontally. They go up to a maximum point, then they come down. So we assume that somewhere in between time 2 and time 3, there must be a height greater than 72. So maybe at 2.5 seconds, it reaches 73 feet. We can be more precise in just a moment on our calculator, but we do know that the vertex is going to happen somewhere in between those times. For now, we're just approximating. So we were able to see the y-intercept. We're able to approximate the vertex from our table of value. And the reason we were able to do that once again from the previous investigations is because we noticed that there is symmetry or sameness somewhere in between time 2 and time 3. We're seeing the repeat measures of 72, the repeat measures of 56, the repeat measures of 24. The catapult arm starts 24 feet high, launches the pumpkin, it increases, then it decreases until it hits the ground. That's a little bit weird because it wouldn't go into negative measured amounts, so it must be hitting the ground somewhere in between time 5 and time 6, in between positives and negatives is 0. So the root, or the x-intercept, must be happening once again on an interval in between time 5 and time 6. And that is what we notice when we investigate the graph. And in between time 5 and time 6, it seems to be hitting the ground. We'll have more precise ways of determining that later on in the course. For now, axis symmetry is the time when the vertex occurs. We assume it's about 2.5 seconds into flight. We approximate the vertex to be measured at 73 feet after 2.5 seconds. We can identify the roots from the table of values as well as the y-intercept. If you were to graph this on your calculator and you went to your function list, you would substitute in negative 8x squared plus 40x plus 24. Once you substitute the expression into your function list, you can take a look at the graph and make the observation of how hopeful launch is flying throughout time. And if you wanted to get a better idea of what the vertex is, you could calculate the relationship at that time. Second trace will help us determine the value, choice 1. And if we substitute in 2.5 seconds into flight, we can hit enter, and it would suggest that frightful flight is still on its way up, and it's measuring approximately 123 feet. If you scroll down using your down directional arrow, it'll jump to go far, which is still on its way up as well, and is approximately 97.5 feet into its flight. And if you scroll down one more time using your directional arrow key, it'll tell you that hopeful launch has reached its maximum height of 74 feet. And again, we can make those observations a little more accurately as we work forward in the worksheet. On the last page, we were actually taking the opportunity to match our algebra with what we saw in the table of values and what we hope to have investigated in the graph, in the picture. And the first thing we did was we took the time to look at the relationship in standard form and compute the value of the axis of symmetry and the vertex using the incredibly powerful axis of symmetry formula determined from calculus. In order to do that, we had to identify the coefficients A, B, and C. For frightful flight, there was no C coefficient, which was fine. We substituted in the negative of B divided by twice A, and we computed that to determine that 4 seconds into flight, algebraically, frightful flight should reach its highest point. To determine what it measured at that point in time, we substituted 4 in place of the x variable, and we evaluated on our calculator. You could simply type the entire expression into your calculator and hit enter. You could simply type the entire expression into your calculator and hit enter, and your calculator will suggest that the expression evaluated 4 seconds into time, or when x equals 4, reaches a maximum height of 144 feet, exactly what we saw in our graph as well as in our table of values. The same thing would be true for go far. Identifying A and B appropriately, substituting into the formula and evaluating tells you that go far reaches its maximum height after 3 seconds. Evaluating the expression 3 seconds into flight by substituting 3 in place of x, I covered it up a little bit, would determine that it reaches 100 feet and that the vertex happens 3 seconds into flight at 100 feet. The axis of symmetry is x equals 3. That's when it actually reaches its maximum value. If we were to do the same thing for go far, we would have to identify the coefficients A, B, and C. A is negative 8. It's the lead coefficient for any relationship. It always belongs to the highest exponential term. It tells us that this quadratic is going down quite fast, 8 times faster than typically would be the case. B is positive 40, and C is 24. If we substitute into the axis symmetry formula, we're able to determine that we have the negative of 40 divided by twice A, which is negative 8. When we simplify that expression, we get negative 40 divided by negative 16. You could have done the entire computation on your calculator, but I'll pick it up from there, where I divide negative 40 by negative 16, and a negative divided by a negative should be a positive, and I'm able to determine that hopeful launch is going to reach its maximum height after 2.5 seconds, exactly what we saw in the table, what we approximated in the table, and what we approximated on our graph. But now we have a more precise measurement using algebra to determine the actual value. Now that we know when it's going to reach its maximum height, we could evaluate the relationship at 2.5 seconds, substituting 2.5 in place of x. So we have negative 8 times 2.5 squared plus 40 times 2.5 plus 24. And by evaluating the expression or the function at 2.5 seconds, we can get a precise measurement of exactly how high this catapult is going to launch the pumpkin in that interval of time. So we substitute into our home screen of our calculator -8, substitute using parentheses, times 2.5 squared plus 40 times 2.5 plus 24. And when we evaluate the expression, the launch of this pumpkin in this catapult at 2.5 seconds into flight, when we believe it's going to reach its highest point, it says it reaches 74 feet. Exactly what we are able to determine on our calculator a moment ago, and pretty close to what we approximated both in our table and in our graph. So the vertex for hopeful launch is going to happen 2.5 seconds into flight when it reaches a maximum height of 74 feet. And you can imagine how that would be incredibly important for so many different scenarios in life where we're trying to determine either the maximum or the minimum value of a relationship. As we scroll on down, the second task we did algebraically was we computed the y-intercept from a relationship in vertex form. Now, the tricky thing about vertex form is it's awesome because vertex form shows us the vertex, but it doesn't allow us to see the y-intercept, the value times 0. That's reserved for standard form, descending exponential order. In descending exponential order, as we were presented with a moment ago, the c coefficient will always be the y-intercept, it'll be the value at times 0. But in vertex form, where the numerical values indicate the vertex when it reaches its highest point, we're not able to see what it equals at times 0. Now, there are a lot of investigations you can make as you get more used to vertex form. A will still be the lead coefficient, and A will tell us whether the relationship is going up or down. So since A is still -8, we know that this is going down over time. It's decreasing, reaches a maximum height, comes down. We could observe the vertex, which is real simple. In vertex form, we're seeing the opposite of the unit of time when it reaches its highest or lowest point. We identify that as -8, meaning the opposite of the horizontal shift. We'll talk more about that as the year goes on. And we're seeing the actual measured amount at that time. Vertex form shows us the vertex, and it's really powerful. So by observing vertex form for hopeful launch, we can identify that at 2.5 seconds into flight, it reaches 74 feet. You could use your calculator to assure yourself that we're getting an equivalent form by substituting this relationship in -8 times x less 2.5. Close off the grouped quantity, make sure you square it so that it's quadratic, and add 74. And if you were to investigate your table of values, what you notice is that the fourth and fifth columns, y4 and y5, are identical. Because what we're seeing is that the vertex form or presentation of hopeful launch is identical to the standard form. And you'll learn how to do that as the school year goes on. But we do love vertex form because I couldn't have made any of these questions without it. It's incredibly powerful. Prior to Common Core having us use this for you algebra students, we really didn't have many real-world examples. It was impossible to make them pretty much without vertex form. The other thing, so the only complication with vertex form is we cannot see the y-intercept. The y-intercept is known as the value of the relationship at time 0. So we're looking for h of 0, and h of 0 is not shown in vertex form. The cool thing about vertex form is we see the vertex, but we can't see the y-intercept. So we'd have to compute what is the value of this relationship at time 0. And we'd have to do -8 times 0 less 2.5 squared plus 74. And if we evaluated the relationship at time 0, we could algebraically determine what the y-intercept is. Now, there are other ways to do that. You could be staring at the calculator screen right now and being like, Tooch, if I just look at the table of values, don't I see that at time 0, hopeful launch measures 24? You could, but the idea is that you practice the algebra. And in practicing the algebra, the expectation is that you would go to your home screen and you would substitute in -8 times the grouped quantity, 0 less 2.5 squared plus 74. And the hope is that when you evaluate that appropriately, it does in fact say that it measures 24 at time 0. So we're able to compute algebraically that the y-intercept from vertex form measures 24. The value of the relationship at time 0, y-intercept, is 0, 24. Lastly, ladies and gentlemen, we could ask you to determine the relationship at any point in time. Evaluate the function at some point in time. So we're asking students in part 5 to determine the height of the function after 3 seconds. Evaluate when t equals 3. So technically that would say f of 3 if we wanted to abbreviate this, or g of 3. We would just say g of 3 equals, and you would have to know that that means I have to determine the relationship at time 3. If you substituted that in algebraically in place of t in standard form for go far, you'd have to evaluate. You could just put that on your home screen and hit enter when t equals 3. And you'd find out that it reaches 100 feet. That happened to be the vertex of go far, and we kind of knew that already. Frightful flight at time 3 is still on its way up. So when you evaluate it at time 3, it reaches 135 feet. And if we do the same thing for hopeful launch, that would require us to put 3 in place of x, or in this case t. So hopeful launch after 3 seconds would equal -8 times 3 squared plus 40 times 3 plus 24. And if we evaluated it algebraically, we could go to our calculator on our home screen and substitute into the expression for hopeful launch 3 in place of t, and evaluate. When we do that, ladies and gentlemen, we're going to get that hopeful launch is on its way down. It has reached its vertex of 74 feet, and it's starting to decrease. It's down to 72 feet. So hopeful launch, evaluated after 3 seconds, is 72 feet high. And some people would write that as a coordinate point, 3, 72. Now, there are other ways you could have made that determination depending on how the question was asked and what you had available to you. You could have simply observed your table of values and said, Tooch, why didn't I just look when h is 3 in my table? And you wouldn't be wrong if you wanted to make that consideration. That's 100% correct. So a lot of students, depending upon how the question is asked and what resources they have available to them, if it were a test or a homework, would just go to 3 seconds and say, it's right there, Tooch, it measures 72 feet. And that's fine. That's what we want you to do. We want you to be able to use the multiple different ways of investigating relationships in this class. We never had that when I was a kid. We kind of had one way, but you guys have so many different possible ways. Algebraically, after 3 seconds, hopeful launch is 72 feet high. In the table of values, after 3 seconds, it's 72 feet high. And something I hope we get a little better at this year, you could have also made the observation graphically. If you investigated your graph and you did second trace or calculate, you could have used choice 1 to determine the value, and you could have substituted in 3 seconds and hit enter. It would have told you that frightful flight has reached 135 feet, exactly what you see algebraically when we evaluate frightful flight after 3 seconds. It shows that go far has gotten 100 feet high, it's reached its vertex, and as we go down to hopeful launch, it shows us that it is in fact 72 feet high. So this is a really powerful lesson, ladies and gentlemen, one of my favorite of the year. It puts together so many of the different ways we're able to make our investigations into mathematical patterns and relationships that we're hopefully going to be using in the real world. Otherwise, we're wasting our time. And it sets the foundation because everything you do throughout this course and all the other possible courses you could take throughout your mathematical career will use the same processes. If you get good at them now, you can be fantastic in algebra 1, in algebra 2, in pre-calculus, calculus, and beyond. I hope you enjoyed the lesson. It truly is one of my favorites of the year, and I'll catch you all in class. Be well.